Okay. And so what we will do will be go over these questions that were on the test one after another, then go for the comparison test. Now, how do we answer the first question? Find the limits. There's no proof, so you just need to use the rules that we use in this class to figure out what the limits are. Let's go by the first one. And so one was find the limits and so we had limit as n goes to infinity of square root of 9n to the fourth plus divided by n cubed, and that was plus something, plus 2. And the way we compute this limit is simple. We take the powers, the highest power of n, so that is square root. We drop everything except that, 9n to the fourth over n cubed. That gives us limit as n goes to infinity. Square root of 9 is 3. Square root of n to the fourth is n squared divided by n cubed. And this is limit as n goes to infinity of 3 over n, and that's 0. For the second one, that's the question where I ask to use the rules that we had for the given question in class to find limit of 1 minus 7 over n to the power n as n goes to infinity. What we do is that we said this is an, 1 minus 7 over n to the n, and we define bn as natural log of an, and that is n natural log of 1 minus 7 over n. Then you're going to take limit of bn as n goes to infinity, and limit of bn, when you try to do that, that's limit as n goes to infinity of n natural log of 1 minus 7 over n, which is something of the form infinity times 0. That's undefined. Therefore, the rule says multiply that second one by the inverse of the first one. So that's natural log of 1 minus 7 over n. So you use L'Hopital's rule. And that's limit as n goes to infinity. And L'Hopital's rule says take the derivative of that bottom. That's minus 1 over n squared. The derivative of the top, derivative of negative 1, a natural log of 1 minus 7 over n squared. That is 7 over n squared divided by the function that is inside. And when you do that, where you get the negative 1 over n squared cancel. You get limit as n goes to infinity of negative 7 over 1 minus 7 over n. And when you take that limit, 1 over n is 0. So this limit is minus 7. And because this limit is minus 7, limit of an is e to limit of bn, which is e to the minus 7. That's how it gets computed. Anything else that you do is out of the scope of this class at this point. There might be other topics where you will be taught how to do otherwise. Now, question number 2 was, show that the sequence is monotonic. Show that the sequence is monotonic. The way you show that a sequence is monotonic is either show that an plus 1 minus an strictly larger than 0, or an plus 1 minus an strictly less than 0, or you show that an is a function of n and f prime of n is strictly positive, or f prime of n is strictly negative for all n's. There's a choice. Either you do that or you do this. Now in this problem, we had an equals n squared over n squared plus 1. So f of n is n squared over n squared plus 1. F prime of n, that's a derivative. That's 2n times n squared plus 1 minus 2n times n squared over n squared plus 1 squared. And when you do that calculus, you see that you get 2n over n squared plus 1 squared. And this is positive because 2n is positive, n squared plus 1 squared is positive. That's it. Just take that derivative, you found out it is positive, then an is increasing. So it's monotonic. In question 3, we're asked to find Sn and limit of Sn. Then answer the question, does the series converge?
Can you scoot your paper a little up?
So, does this series converge? So that's the question. It's 3 pieces, and most of you actually didn't see the third piece. First piece is find Sn. It's a question by itself. Find limit of Sn. Does this series converge? Actually, this is actually a hint for you on how to answer this question. Because to answer this question, you need to find Sn, find limit of Sn, and decide whether it converges or not. Now, here, in this problem, if this is an, you can see that's an plus 1. So that's sum of an minus an plus 1. So it's a telescoping series. So this is a telescoping series. Sn, in this case, is going to be a1 minus an plus 1 when you write down the terms. And a1 is obtained by plugging in 1 for n in that an. So ln of 1 is 0. Let's first put ln of 1 minus ln of 1 over n plus 1. And so you would say this is equal to actually ln of n plus 1, because negative ln of 1 over n plus 1 is ln of n plus 1. So that's Sn equal to the natural log of n plus 1. Limit of Sn as n goes to infinity equals to limit as n goes to infinity of natural log of n plus 1. And natural log of n plus 1 goes to infinity. Because this limit is infinity, the series diverges. That's the reason why it diverges. Because the limit of the partial sums is infinity. And that's it for the first 3 questions. Now, the next question is about sums. Find the sum, find the value of the series. Question says, find the value of the series. And the series is sum, and from 0 to infinity, 3 to 5th to the n minus 4, 3/7 to the n. That's the easiest possible geometric series you could get. In this case, you would say, okay, this sum this series is equal to 3 over 1 minus 2/5 minus 4 over 1 minus 3/7. That's the easy answer, because the sum of a geometric series is a over 1 minus r. Sum of geometric series, a over 1 minus r. So that's geometric series. And when you do that algebra there, you get, in this first one, 5 minus 2 is 3. You get 5 minus 7, because 7 minus 3 is 4. 4 over 4, they cancel. So the answer is minus 2. And then question 5, decide whether the series is convergent or not. So sum 5 over n cubed, and from 1 to infinity, converges as p series, p equals 3 larger than 1. Second one, sum n equals 50 to infinity, 2 over n. This diverges as tail of P series with P equal 1. P series with P equal 1 diverges. And I call that a tail because we don't start at 1. We start at 50 going on. Then C, sum n from 30 to infinity, 1/2 to the n. This converges. And you can say geometric. Where R equals 1/2 is then 1 in absolute value, right? That's it for number 5. And now number 6 says use the divergence test. And the series is sum n from 1 to infinity, 1 minus n over n cubed. So the divergence theorem says find the limit of a and 1 minus n over n cubed. This limit is limit as n goes to infinity minus n over n cubed. And usually in calculus, what we do say is the power of the bottom of the top is lower than the power of the bottom. So this is going to be equal to 0. So the limit being 0, the test is inconclusive. That's all you need to do in the question, nothing else. Now use the integral test. It was question 7. And it says sum n from 3 to infinity, 3 over n to the 3/2. First of all, to use the integral test, you need to remind yourself what are the rules. So here f of x is 3 over x to the power 3/2, which is positive. F prime of x, you find it minus derivative of x to the power 3/2. It's minus with the minus here. 3/2 comes, down, so that's going to be 3/2 times 3, 9 over 2 x to the power 5/2. That's what you will get as derivative here. Using the power rule, because x to the 3 over x to the 3/2 is 3 times x to minus 3/2. You take the derivative by getting the power down, negative 3/2 goes down, and then the power becomes negative 3/2 minus 1, which is negative 5/2, so it goes back to the bottom. And negative 3/2 times 3 is negative 9/2, and you can see that that derivative is negative because it's negative 9/2. This is a positive number. X to the 5/2 is positive, so with the negative sign in front, it's negative. So here you do have f is decreasing and continues on the interval that is concerned from 3 to infinity. So you can compute your integral. Integral from 3 to infinity of f of x dx. It's integral from 3 to infinity of 3 dx over x to the 3/2, which is integral from 3 to infinity of 3x to minus 3 halves dx. And this integral is 3 times x to minus 1 half, which is minus 3 halves plus 1 over minus 1 half. Compute this from 3 to infinity. So minus 1 half goes up, that is 6. When you plug it infinity to the power minus 1 half, that's 0. Minus minus becomes plus, so you get 6 over square root of 3, which is nothing but 2 root 3. So that integral is finite. That's the most important thing. So you can conclude that this series converges. That's it. Then you head to question 8. Root test. And the root test was for sum n from 1 to infinity, 1 half minus 1 over n over n. So an is equal to 1 half minus 1 over n to the power n. And this an is larger than 0 for n larger than 1. And the nth root of an is a simple function, 1 half minus 1 over n. So limit as n goes to infinity of the nth root of an is limit as n goes to infinity of 1 half minus 1 over n. And you plug those numbers in. 1 over infinity is 0, 1 half minus 0 is 1 half, and 1 half is less than 1, which implies that the series converges, full stop. Then you get 9, a ratio test. You get sum n from 1 to infinity, 3n cubed over 100 to the power n. And that's 100 to the power n, not 100n. And so to use the ratio test, you got an equals 3n cubed over 100 to the power n. This is positive. An plus 1 is 3n plus 1 cubed over 100 to the power n plus 1. And then an plus 1 over an. This is equal to 3n plus 1 cubed over 100 to the power n plus 1 times, we multiply by the inverse of this, so that's 100 to the power n over 3 times n to the cube. So what I do understand is that some of you have issues with algebra. You understand how to simplify. You can only simplify things that look alike. That's 3, that's 3. You can cancel the 2 3s. That's 100 to the power n, 100 to the power n plus 1. So we can get rid of 100 to the power n. It remains 100 down there because you cut 100 to the power n from n plus 1. So you remain with n plus 1 over n cubed times 1 over 100. And the limit as n goes to infinity of an plus 1 over an is therefore equal to 1 over 100. Why? Because n plus 1 over n cubed has limit 1. And this number, 1 over 100, is less than 1, which means that the series converges. That's it for all the rules that you had for series. And then you had the last question about bounding Sn S minus Sn using the form the bound on the remainder in the integral test. That was on question 10. So we do have to answer that question. You have integral from n plus 1 to infinity f of x dx less than or equal to s, and even strictly less than s minus Sn, less than integral from n to infinity of f of x dx. That's what we use for it. So to answer the question, what you needed to do here, find an upper bound and a lower bound for s minus Sn was to compute this integral and compute that one. And what I did show in class was you don't need to compute it twice. You just compute this one, and then you replace n by n plus 1 to obtain that one. So that's what we do. So integral from n to infinity. And in this case, f of x was given in the problem as 2 over n cubed. And the numbers that are selected are very important because you use the wrong numbers, you get the wrong answer, and you get something that is complicated to handle. So 2 over x cubed dx, this is equal to 2x to minus 3 dx integral n to infinity. And when you integrate x to minus 3, what you get is minus 3 plus 1 minus 2 over minus 2. The 2's cancel. So the integral is minus x to minus 2 from n to infinity. And when you plug in infinity, you get 0. You plug in n, you got 1 over n squared. That's what it is. 1 over n squared. And when you replace n by n plus 1, you get 1 over n plus 1 squared. So you have 1 over n plus 1 squared less than or equal less than s minus Sn less than 1 over n squared. Those are the upper bound and lower bounds that you were asked for. And now to answer, to finish the problem, the last part said, find the smallest value of n for an error less than 10 to minus 4. It's not the lower bound that you're going to take, it's the upper bound that you're going to take to answer that question. So that is going to be 1 over n squared less than 10 to the minus 4. So to answer that last part, you answer 1 over n squared less than or equal to 10 to minus 4, which leads to n squared larger than or equal to 10 to the fourth, or n larger than or equal to 10 squared, which is 100. So you need at least n equal 100. All right, any questions on this? Is there any question on this test now at this point? Is anybody here?
Yeah, I hear you. I just don't have any questions.
Okay. Do we have questions, Kazaa?
No, I don't.
Gage?
Yeah.
Is there any question?
I don't have any questions.
Okay, so the only thing I can say for those who didn't do good on this is the final exam usually replaces your worst test grade, but that can only work if after making a mistake, you make sure that you learn and understand the material before the final exam, because similar questions are going to show up on your final exam. Your final exam is going to cover topics from all 4 tests that I give you in this class, all of them. So if you mess up on test 1 or on test 2 or on test 3 and you don't review as we do, that's why I always come back and review fully the test, because you still need them. Don't say I'm done because I didn't work on it. That's fine. Let me continue. It's not going to work that way. If it didn't work, go back, review that, make sure you get it and you know how to do it while we're moving on. Because by the time we get to the final exam, there will be many topics accumulated. And if you didn't get all of them, it's going to be hard to prepare for the final exam, right? So from time to time, you can have a look at the things that you didn't get right. And even if you did do it at 100%, don't sit there and think I already know all of it. You might forget. So from time to time, still make sure that you're keeping track of the things that we are doing. It does happen. It can happen to anybody. It can happen to me. It can happen to you to forget something. So make sure you always keep an eye on the things that you do until you finish with that final exam. After the final exam, you could say, hey, man, I don't need this anymore. And you throw away even the book, right? At that point, because you don't need it anymore. But before we end, please make sure you keep your hands on the things that we are doing. All right. Again, the next test will be coming after your homework 2. And the homework 2 will be posted online this week. And you will have, as I propose, enough time to start answering the questions on the topics that we cover in class as we go. I don't need to see you submitting that homework online because it's not graded online anyways. So what you need to do is just up and scroll through the topics and see the problems that are related to the topics of the day and try to answer them. If you cannot answer them, you can bring questions. We discuss your questions and then we move on, so that by the time we get to the day you submit it, you already know how to do what is inside there. But if you don't and you keep it to the last day, you might be surprised to open and see maybe 15 problems that you need to solve in 1 hour. At that point, you understand that it's hopeless. So don't do that. Any questions in general before we move on? No? Autumn? Is she with us? Are we good, Eric? Casey? All right. Okay, if there's no question, then let me head back and just start doing comparison theorems. We do the comparison test. So that's a new material, comparison test. There are two of them. The first one is just called the comparison test, and the other one is the limit comparison test. For series. So how does the comparison test work? So you have we have sum n from something, doesn't matter really. So from say a to infinity of an. This is what you have and need to decide whether this series converges or diverges. So that's the setup. And now this has to do a lot with your skills and your knowledge of functions, because you get the series that is written there with an, and you must cook up another series that you already know how to handle. And that's why often I like to put this topic after testing you on the other topics, because all the other topics that we had before this actually come into play in this single topic here. Because when you're cooking up that series, you need to have in mind the other test that you can apply on the new series that you're creating to decide whether that series converges or not. How is it used? So how is this method used? One, you must have a correct feeling, and this is really strange, right? You must have a correct feeling of whether the series converges or diverges. If you don't have that, you can't start the problem. You need to have an idea whether this thing converges or diverges. Second, need to build an appropriate series, sum of Bn. Such that we know how to decide for its convergence or divergence. So the series that you are building, looking at the one that you have, you must know how to decide whether that other series diverges or converges. Moreover, third point, if you feel that sum of an diverges, then you must build sum of Bn that diverges, and Bn is less than An. These are the key points. If you have the feeling that the sum of An diverges, then you must build a sum of Bn that diverges and that is below An. That's part A. And the B, if you feel that the series sum of An converges, then you must build sum of Bn that converges, and in this case An is less than Bn. And above all, what you need to do starting with is here that your Ans are positive, as in all the other questions that we have been handling now. And the Bns that you're building will also be positive. So these are the rules for the comparison test, okay? So first, you need to have a feeling of what's going on with the series. You need to feel whether it's convergent or divergent. If you decide that it's convergent, that must be based on your knowledge of another series Bn that diverges and that is smaller than An. If you have the feeling that the series converges, then you must be able to build another series such that its sequence is above An. Does this make sense? So it's a two-way thing, right? Any questions about this? This is the philosophy behind behind the method, right? Before you go to apply it on a concrete problem. Any question? Okay, if you have no question, let me show an example here. Use the comparison test. Or sum, okay, from 1 to infinity, 1 over 9k to the fourth plus 3, for example. Okay, I give you this. And so this is the AK. And when we look at this, what do you think? What would you feel? Do you feel this thing would diverge or converge?
It would converge.
You would feel it would converge. Why? What do you think to compare it to so that it tells you it might converge?
I would compare it, I guess, to the reciprocal fraction.
Yeah, because you can see there k to the power of 4. So right away you're thinking p series in this case, right? That's what you're thinking about. So, and then you say, okay, this thing might converge because it almost looks like a p series with p equal 4, right?
Yeah.
Okay, now, because the method is comparison test, you want now, because you're thinking that it's convergent, you want to build, so you have AK equals 1 over 9k to the fourth plus 3. And you want to build a sequence that is larger than this one, whose sum is convergent. So what is this thing less than? What can I put on top of this function? Just looking at it. And in this part, most of it will be your skills.
That function would be less than 1 over 9k to the third.
That's correct. That's less than 1 over 9k to the third. As I said, it's going to be your own skills because you feel 9k to the fourth plus 3 is larger than 9k to the fourth. So the reciprocal is going to be less than this. And nobody can give you a general formula for everything. You should feel the thing that you are seeing in front of you. And even this one, I can make it smaller than something else. Tell me.
1 over 9k to the third.
Don't reduce the power.
Would it be 1 over k to the fourth then?
1 over k to the fourth, great, because 9 there, I don't need to be wasting my time with the numbers that are going to disturb me. So I take it out. So it's less than 1 over k to the fourth. That's true. So these two inequalities are true. So I'm going to take this guy as bk. And sum of bk equals sum of 1 over k to the fourth, k from 1 to infinity. Now tell me, does this thing converge? Sum of 1 over k to the fourth, does it converge?
Yes.
Why?
Because the limit of that would go to 0.
No, that's not the reason. We said it before even doing it. What's the reason why sum of 1 over k to the fourth converges? What kind of series is this?
Because it's a p series with p greater than 1.
That's it, because it's a p series with p greater than 1. So this converges. Sum of bk's converges as p series with p equal 4 larger than 1. And thus, sum of AK converges. That's it. That's how you use the comparison test. I was able to build a larger sequence that gives a converging series. Therefore, the sequence that was below gives a converging series. That's this B case. When you feel it is convergent, you build something that converges on top. You felt it was convergent, we build together something that is on top and whose series converges. Therefore, we conclude that the one that was given is convergent. So it's always about these two things. One, being able to have the right feeling and build the appropriate series. Decide whether it converges or not based on that. And if somehow you put on top here a series and you find out that this sum here diverges, in this case, for example, if I found out that this sum diverges, then that will be useless because I put on top of a convergent series something that diverges. It doesn't tell me anything about it. That's why you need to be very careful. Okay? This, if I want to decide convergence, I must create a convergent one that is larger than. If I create a divergent one, I've wasted my time. The comparison test is not going to work. The same thing works for divergence. If I want to decide that it is divergent, I need to put below a divergent sequence. But if I put up below a convergent sequence, I've wasted my time because I'm not going to be able to decide based on the comparison test. Am I making sense?
Yes.
Jesse, are you with us? Can you hear me, Mr. Kessler?
Yeah,
Are we good?
I'm good.
All right. Okay, so that's the thing. Let's look at another example. And please, I do recommend that as soon as possible, you work out the examples on this. Otherwise, you're gonna forget, and in 2 weeks when the test comes, it's gonna be like new life. Now, let's look at another one that is similar to this one before we change topic. So, example 2, we got sum k from 1 to infinity, 1 over 8 k to the power 4/5 minus 2. Now tell me, what do you think of this one? Do you think it will be convergent or do you think it will be divergent? And I say it's similar to the previous one. So you're thinking in terms of P series.
Would this one be divergent?
You would think it is divergent because if a P series comes out of this thing, it's going to be k 1 over k to the 4/5, and 4/5 being less than 1, you think it's going to be divergent. That is correct. And now our job is to see how to build that function that is going to be below this thing. So we start ak in this case is 1 over 8k to the power of 4/5 minus 2. And I want to put something below this function. What is below? What do you think is going to be below this?
Would it just be k to the 4/5?
Be very careful at this point. If you jump something, you might miss something that you don't see, and it will mess up everything. What function is immediately seen to be less than 1 over 8k to the 4/5 minus 2? Look at what we just did. Just go one step.
1 over 8k to the 4/5.
1 over 8k to the 4/5. That's the first step. So this thing is going to be less. 1 over 8k to the 4/5 is going to be less. Why? because 8k to the 4/5 is larger than 8k to the 4/5 minus 2, the same rule that applied in the other problem. Now, in this problem, which is the remark I was making, you cannot get rid of this 8 here, because if you get rid of this 8, you're getting a number that is larger than that. So we really can't get rid of that 8. So at this point, this is our BK. And we will see now sum k from 1 to infinity of BK equals 1/8 sum k from 1 to infinity 1 over k to the 4/5. Now, how do we decide here? This thing here is a P series. What is P?
Four and a half.
What?
I mean 4/5.
4/5, good. And that is less than 1. So it diverges. That's it. So we have been able to put below this sequence a sequence whose series diverges. Therefore, we can conclude that this one diverges. Thus, sum of AK diverges. So if I can manage to put below AK a sequence whose series diverges, then I conclude that the series of AK diverges. If I can manage to put above a series that converges, then I conclude that the initial series converges. That's the rule. Any questions? Okay, no question. Then this is the next part. What we call limit comparison test. So if limit as n goes to infinity of an over bn, and you remember we are still talking about positive sequences, of an over bn equals L. L is not 0. L is not infinity. So if you have limit of an over bn equals to L, then sum of an and sum of bn converge or diverge simultaneously. So if you can show that the ratio of the two sequences of two sequences is a fixed number that is not 0 and is not infinity, then when one converges, the other one converges. When one diverges, the other one diverges too. That's what the statement means. Okay? And the second part in there is if limit as n goes to infinity of an over bn equals 0, if this is the case, that means that bn is very large compared to an. Is that true? Then sum of Bn converges will imply that sum of An converges. Notice that here it's not an equivalence. It's this implies that. In the first case here, it says anytime sum of An converges, sum of Bn converges. Anytime sum of An diverges, sum of Bn diverges. When the limit is 0, it's a different story. When this guy converges, the other guy converges. And the opposite of this is if limit of An over Bn is infinity, which in this case would mean that An is larger than Bn. Then sum of Bn diverges, implies sum of An diverges. Because in this case, in these two cases, it actually takes us back to the comparison test. That's why you hear me saying, if this is 0, that means that An is small compared to Bn. If I can divide An by Bn and get 0, that means that An is small compared to Bn, right? And if An is small compared to Bn, then if sum of Bn converges, then sum of An converges. So this is just a simple comparison test. Same here. If An over Bn is infinity, that means that An is very large compared to Bn. Therefore, if the sum of Bn diverges, being small, the sum of An will diverge as well. Okay, so that's how you prove these two things. So how do we apply that? And in this case, that's where most of the time you love to use those p-series, okay? You have sum k from 1 to infinity, 8 over k square root of k plus 6. And we want to know whether this thing converges or not. So how do we do this? My hint here will be look for the p-series. How do you get the p-series here? What will be the power of the p-series here if we try to get some? Ak is 8 over k square root of k plus 6. Give me a hint, please. What p-series can I form from this?
1/2.
What's the power of k here? What's the power of k in this function? That's what the p-series should be. You
It'd be
have
3 over 2 for this one.
good k times k to the power 1/2 because you got k and you got square root of k. So it's going to be k square root of k. That's the power of k that you see there. And that is 1 over k to the 3/2. And sum of 1 over k to the 3/2, k from 1 to infinity, does it converge or not?
It diverges. Oh,
Three.
it converges. I'm sorry.
Good. Converges. As 3/2 is larger than 1, right? So you do have a p-series that converges. And now you can say, what is the limit of AK over BK as K goes to infinity. That's equal to limit as K goes to infinity of, and we can multiply by that, that'll be 8K to the 3 house over K square root of K plus 6. So when we divide, we just multiply by the inverse of this, which is K to the 3 house. That's why I just wrote 8K to the 3 house. And this limit, K to the power 3 house, K to the power 3 house, they cancel. So this limit is 8. The limit of the ratio is 8. It's not 0, not infinity. Sum of bn's converges. Therefore, by the limit comparison test, sum of an converges as well. That's how you use the limit comparison test. Questions? Is there any question on this?
Is the second limit going to infinity? I can't see. Like, is that an infinity sign?
That's 8.
8. Okay.
Oh, you're talking about k going to infinity.
Yes, that's what I was talking about.
It's the same limit we're writing. We're just putting AK and BK, so it's infinity.
Okay, I was just making sure.
That's good. It's good to ask. All right, another example. Now it's for you to tell me what we get here. It's not always a P series that you get out of it. Sum k from 1 to infinity. 7k cubed over 9k cubed plus 6 to the power k. And we say we use the limit comparison test. Or say, man, use any test of your choice. I see a use comparison test. What ideas do you have for this one?
Would you use the root test?
No, it's a limit comparison though. So what do you want to compare this to? That's the thing. What would be your guess? Just as in the other problem, in the limit, when k goes to infinity, what does this thing behave like? The thing that is
7/9.
7/9. So Bn, B or Bk behaves like 7/9 to the power k that is there. And sum of 7/9 to the k as k goes to infinity, k from 1 to infinity, does it converge or not?
It
Hello?
converges
Why?
because it's a geometric series with r less than 1.
That's it. Converges. That's geometric series. Absolute value of r is 7/9 less than 1. So it converges. And thus, this thing here converges. And the reason being that the limit of that whole thing divided by this, the limit of this AK over BK is finite. It's a finite number. It's not zero, it's not infinity. And therefore, we can conclude that the sum converges. And first thing, why is this thing comparable to 7/9? Because when we take the limit, we said we take the highest power of k, right? So that is 7k cubed over 9k cubed. The k cubed cancels. That's why you have 7/9 and the power k remains. Does that make sense?
So when you're determining the limit of the inside function, do we just ignore the power k when taking the limit to infinity?
It is still standing there. We are approximating this thing. We're trying to see what it behaves like. Right? We're not getting the limit. We're trying to get what it behaves like. That thing inside, when k is large, it behaves like 7k cubed over 9k to the 6, because 6 is almost nothing compared to k when k is big. Does that make sense?
Yeah, that makes sense.
So when k is large enough, it's like 1 billion plus 6, man. You don't even notice that 6 is there. And so you ignore that, and these get divided, and you say that the whole thing is going to behave like 7/9 to the power k. And because it's a power, you cannot neglect anything. So it's 7/9 to that raised to that power. That's almost what it's going to be behaving like. Then you use it to compare. And then you show that the other piece is convergent. If it's convergent, then by the limit comparison test, the original one is going to be convergent. Class time is over. So if you want to go, you're free to go. You want to stay and ask questions, feel free to ask. And please do the problems. I have seen that people have not opened that to actually complete and look. It's good to look at it before class and then answer some after class. And in that case, you're not lost completely when you come into class and we start talking about this. Any other questions? Am I right saying that the class time is over?
Yeah.
Okay, good, because I saw that everybody was still here, so I thought maybe I'm wrong. Yeah.
Thank you, Dr. Lonwell.